Okay. All right. Happy Thursday, Thursday week 2. We're going to get into some really great foundational topics today. Get into some nitty-gritty a little bit. Some super important things that will actually, it kind of all builds on itself. Whoa, didn't mean to do that. It all builds on itself. There's little things here and there that we don't really carry through the whole thing, but um, most of it continues to be applicable as we go. So today we're in section 3.2. You will need your fancy calculator. And I have my other one muted and it yells at me, hey, you're muted. I want to be muted. Okay. Section 3.2, we're going to look at the range of the available of the variable of a variable of raw data. I mean, that is basically 2 slides, and then most of the rest of it, almost the entire rest of it, is standard deviation. And then we'll jump into the empirical rule. The empirical rule is really a method of like estimation. And estimation, I mean, estimation is super important. We estimate a lot of things where I'm like, okay, I think this is going to cost me about $30, or I think it's about this many miles or this many minutes to get to this place. Pretty much every day in our lives, we're estimating something. And I know that in my high school, I get mad at kids get mad that I'm talking about, okay, well, we need to know what it is about how much it is. Well, if we can just pull out our calculator and get the exact number, why do we need to know about? Well, because when you're just moving along in life and you're thinking about things and you're talking about things, you don't want to have to pull out your calculator and find out the exact. Being able to give an estimate is really nice. So, anyway, sorry. The empirical rule is a really great way to estimate things, and we're going to be continuing to use empirical rule for the rest of the term. And we're going to be drawing pretty pictures. So, first, we're going to start with range. So range, all it is the difference between the largest and the smallest data value. So you just take the largest data value, subtract the smallest data value, and ta-da, you have the range. That's it. We've got a range of this many values. It doesn't get more complicated than that. So the range is just the largest data value minus the smallest data value. So let's take I already mathed it out for you. So we have the travel times from our previous data set from last last class, and we're just looking at the range of the travel times in minutes of the employees going from this startup web development company. Let's take the highest, which is 43, subtract the lowest, which is 5, and we have a 38-minute range. I think we've probably all used that math in life one time or another where we're just said, oh yeah, it's somewhere in here. It is this range. That's basically what we're doing. All right. So let's get into our big topic of tonight, standard deviation. With the exception of chapters 4 and 5, standard deviation will be with us every single lesson. Chapter 4 and 5 are their own animals, but other than that, every single lesson will be talking about standard deviation. So standard deviation tells us how spread out the numbers are. So it tells us if our numbers are really widely spread out than our data is, then we have a larger standard deviation. Smaller standard deviation, it means that our data values are more grouped together. We will have slightly different formulas for population and sample standard deviations tonight. It'll be slightly different. It's not like with mean. When we calculated mean, it was the exact same formula. Population and sample standard deviations are slightly different. And as I said on probably on Tuesday, as I said on Tuesday, the population gets the fancy symbols. This symbol right here is a lowercase sigma. My lowercase sigma, every time I draw it, it's going to look really ugly, has a lot of character, as all my drawings do. All my drawings have a lot of character because I'm not very good at it. But you know what? If it's all about enthusiasm, I'm an amazing artist. So this looks super scary. Don't worry, I'm going to walk you through it step by step, but it looks super scary. But basically, this is what we're doing. You take each data value and subtract the mean from that data value, and then you square that difference. So you do it with the first data value, you do it with the second, you do it with each and every data value. Take the mean, you take the data value, subtract the mean, and then square it. Then you add all of those squared differences together. Add them all together, and you divide them by the number of observations there are in the population. Since this is population standard deviation, we divide it by the population size. Remember, a capital N represents population size. This symbol right here is a capital sigma. We've got the lowercase sigma that stands for standard deviation. The capital sigma, it means add them all up. And then after you divide by the population size, take the square root of the whole thing. So the reason we square them is because we want to get rid of the negatives, because you're going to have some negative values when you take your data value and subtract the mean. There's going to be some negatives there. We don't want those negatives, because what happens is if you do that with each and every data value and you don't square them, you're going to get a sum of 0, and it doesn't help us with anything. So we want them to all be positive. And then when we add them all together and divide by the population size, square rooting gets rid of the square roots that we did. So it undoes all that squaring that we did previously. Don't worry, we're going to do some of these by hand because the formulas don't make a whole lot of sense until you actually put some numbers in there. But when you go back to it, you'll be able to say, oh yeah, that's what we did. All right. So we're going to step through it one at a time. One baby steps through it. We're going to do the whole thing together. So go ahead and map this out while I do. So the first thing we're going to do is we're going to find the population mean. I think we found this on Tuesday. So I'm just going to really quickly, because we've done this before, I'm just going to really quickly in my calculator, because I don't remember what it is. You probably could get to it quicker than I am, but I am almost there. So 24.9, unless I added it wrong. 23, 36, 23, 18, 5, 26, 43. Yes. So my mean is 24.9. This is the mean. Okay, so now I'm going to subtract the mean from each number, and then I'm going to square the results. So it's going to look like this. So I'm going to take the first one, 23 minus 24.9, then I'm going to square it. I have 3.61. Well, what is that? I did not mean to do that. Oops. 3.61. Do 36 minus 24.9 squared. One 23.21. We already have the 23. I'm going to write it again, but then I'm just going to steal the number from up there. Then I have 18 minus 24.9 squared. $47.61. Do 5. This number's going to be big. It's okay. 615. Did I do that right? Uh-oh, no. 524.9. Enter. That number was not right. 396. I was like, yeah, I put that in the calculator wrong. 0.01. Let me see. 26. This one won't be too bad. Yep, this is a baby one. 1.21. And then 43. My box is just the right size. One might say I might have done this before. Imagine that, 327. Okay, so now I've subtracted the mean from each data value and squared them. So these are all my squares right here. Okay. Uh-oh, let me move that over. I want to move this over so we can see it. Oh, and there we go. All right. Next, it tells me to add those square results together and then divide them by the number of values in my data set. So I'm just going to put those in my calculator and just add them together. Please also do it because I am the queen of typos. If I get the wrong answer, someone's got to save me from myself. Nine oh 2.87. Then I'm going to divide that. There's 7 numbers in my data set, so I'm going to divide it by 7. I'm going to give you a second so that if I made a math error, somebody can fix it before I dive further into this. Move this over. Okay, divide that by 7. So I said divide by the number of values in my data set. I have, 128. I'm going to put 0.98. Okay, finally, the last thing they want us to do is take the square root. Okay, so I'm going to take the square root 128.98. If you don't know where the square root is, you see the x squared button up here next to the comma. Do second x squared, and that'll get you there. It gives you, my standard deviation is 11.36 about. I just rounded it 2 decimal places. It doesn't say where to round it, so I just picked a number. So what the standard deviation tells us, the standard deviation is the average distance the data values are from the mean. That's what we just calculated. The average distance the data values are from the mean. So if that average is bigger, then the numbers vary widely from the mean. I feel like considering our data set, I feel like this is fairly large, but we do have a 38-minute range. And so it kind of makes sense that we would have a little bit of a large standard deviation. Questions before we move on? All right, we're going to do another one. We are going to do the test scores. So what I would like you to do is I'm going to work quietly behind you. Our mean for this one, our mean was 79. That one I have memorized. That one's in my noggin. I would like you to take each data value, subtract the mean, and then square it. So go ahead and start. I'm going to work quietly behind you. So I would like you to practice. I'm going to step you through it. So I'm not saying, hey, do all of it at once by yourself. Just do that part. If you're comfortable, once you find these, go ahead and start working on the rest of it. If you're not comfortable, feel free to just wait. Give y'all a minute to do the math. Okay, after you get all of those squared differences, after you get all those squared differences, add them together. So add them together. I'm going to put this right here. Add them. That's the first thing. Then you're going to divide by capital N. So our population size, in parentheses, that's 10. There are 10 of these test scores. Divide by the 10 and take the square root. And that'll be your answer. So go ahead and work through that. Yes, perfect. Good job, Amanda. How'd we do? Do okay? Questions on calculating it? Yes, good. Good job. Good job, Rebecca. Yay. Yay, Kiana, good. Looks like we're getting some good answers. Yay, that's awesome. So this is population standard deviation. So population standard deviation, we do all of this, then divide by the population size, and then take the square root. So this is by hand. Yay, all right, good. Good, good, good. Woohoo. I'm here to cheer with you. I love it. This is a very, very tedious process. After we do sample standard deviation, I'm going to show you how to make it easier in your calculator. And the hand in homework is going to require you to calculate standard deviation by hand twice, once for population, once for sample. After that, you never have to do it by hand again. After that, you can just use your calculator. Now, some people like to do it by hand, and feel free to do it, but I'm going to show you how to do it on your calculator after we do sample. Okay, sample standard deviation. So, as I said, the samples get the boring symbols. Lowercase s is what we use for our sample standard deviation. Now, the meaning of it is still the same thing. We're just using a sample data set instead of the population. So, a long, long time ago in the land of last Tuesday, 2 days ago, I showed you, we looked at all of the different sample means that we can get. Remember, we all calculated sample means, and they were all over the place. Now, sample standard deviations would be the same way because of you not knowing what sample you're going to get or how close to the actual standard deviation you're going to be. You're going to be all over the place because of different samples and how random they are. Because of the variabilities of samples, we have to account for that little bit of error. So we're kind of like erring on the side of caution. So the process is exactly the same, except this piece right here. We are dividing by the sample size minus 1. Dividing by n minus 1 degrees of freedom. Don't worry about what this means right now. We're going to talk about that in, I think it's chapter 10. Might be chapter 9. But we're going to be talking about that. Actually, pretty sure it's chapter 9. So we're going to talk about that way down the road, but just take the sample size and subtract 1 from it. That's what we're dividing by. It's because of that variability that happens from us having a sample. We're just kind of trying to make up for that error a little bit. So the sample standard deviation will always be a little bit higher than the population standard deviation. It's okay, it's expected, it's what we do. So let's calculate a sample standard deviation. This one's wee little standard deviation. This one's small. We're just going to use 3 data values. So first we need to find the mean of these 3. I'm just going to do this on my fancy calculator. So I got 67 divided by 3. So my X bar, remember X bar is what we use for sample mean, is 22.3. Okay, that's good. So we're going to use the exact same process except for that one little difference. Okay, so I have 5 minus 22.3 squared. $299.29. It's a big number. 26 minus 22.3 squared. $13.69. And 36 minus 22.3 squared. 187.69. Okay, once again, I'm going to add these together. Except for apparently I can't. I'll keep typo queen. Rides again. Okay, I got 500.67. All right, so now we're going to take this 500.67. We're dividing it by n minus 1. So we're going to divide it by 2. Because our sample size is 3, so we divide by 2. I have 250.34. Now we take the square root of that number. So everything's the same except for that n minus 1. So our sample standard deviation, which is a lowercase s, 15, well, I was 15.8. I was going to write 18.5 as I said 15.8. That's it for sample standard deviation. Questions? Okay. I think,
I have a question.
Where
oh,
did you
sorry.
get the 2 again? Is it scrolled up on the page and we just can't see it?
No, it's right here. So there's 3 in my data set. So it's
Uh-huh.
n minus 1. So my n equals 3. So n minus 1 equals 2. So I just divided by n minus 1.
Okay.
Right. Was there another question?
That was my question.
Okay. So hopefully that made sense. Okay, I think, okay. We're not going to go there right now. What we're going to do now is I'm going to show you how to use your calculator. We're going to use, let's use the student data right here. So everybody pull out your fancy schmancy. I'm going to go to my screen that has my fancy schmancy on it. There we are. Don't want to exit full screen. All right. So if you've never used this type of a calculator before, other than basic calculations, it's okay. I'm going to walk you through it as if you've never seen it before. So most people that make it to this class have never used one of these before. So I'm going to act as if you've never seen one before, other than just basics. And then, so make sure you stop me and ask questions if you have them. So the first thing we need to do is we need to put our data into the calculator. We're going to put it into a list. So you're going to hit this button right here. So we have, I'm always going to call this like arrow keys or the circle arrows or arrow circle or something like that. So right next to the arrow circle is the stat button. It says stat, and we hit enter on the stat. We have all of these options. The only one I'm ever going to use is number one on this particular screen. On this screen, the only one I'm going to use is number one, and I'm going to hit enter. You should be on a screen now that has lists. L1, L2, L3, L4. So it has lists on it. There might be stuff in your lists. If there is stuff in your list, you're going to use this up arrow here so that L1 is highlighted, and you'll hit the clear button. Do not hit delete. Hit the clear button. Hit clear and then hit enter, and it gets rid of everything in there. I'm going to do it again. I'm just going to put some random numbers in here. Okay, once again, you arrow up and then you hit clear and then enter, and it will clear it out. Now you'll have these nice, pretty blank lists. Now, if you
Hold
accidentally,
on,
yes,
I have a question.
yes,
Sorry, I
no,
I
it's
was
fine.
writing when you did the very first step to get
Okay.
there.
All
What
right.
was the very first calculator
Okay, let
step?
me get out of here. So we're on this screen. This stat button right here next to my circle,
Okay,
stat, and it's the first option.
got it.
Okay. Do you need me to clear the list again, or are you good?
No, I'm good.
Okay, perfect. All right, so that's exactly what I want. Make sure you stop me if I lose you, because these calculators can be overwhelming and I don't want to overwhelm anybody. So now we're just going to put the data values in here. So just put each one in and hit enter. So just put it in and hit enter, and it'll just keep going down. I'm just putting in the test scores. And I am queen of typos. Most common error is typos right here. Every single time I put values in, I will go back up and I'm going to compare each one with my list to make sure I didn't typo, because I tend to try to do it too fast and bad things happen. Okay. I'll give you a second to make sure that you get all of yours in there. And I know you have it on your PowerPoints and whatnot, but I don't want to leave anyone in the dust. Okay. So now if all your data values are in there, we're going to hit the stat button again. We're going to just hit stat again. It gets us back to this screen. Arrow to the right so that calc is highlighted. What we want is one var stats. This stands for one variable statistics. We have one variable. Our variable is test scores. We have one variable. We want one variable statistics, one var stats. You're going to hit enter. So we put our data into list one. So if you put it into a different list, which I don't think you did this time, but if you did, you can change this. So if I wanted it to be list two, or if this already said list two, so down here, I'm gonna see if I can zoom in. So look here underneath the numbers. So look at the blue in the top corner of these numbers. This is list numbers, list one, list two, list three, list four, list five, list six. So you can choose whichever list yours is in. So if mine is in list one, so I would do second one, and it puts L1 there. If it was in list two, I would put second two, and it puts L2 there. I'm going to go back and put L1 in there again. So whatever list it's in, you do second and then the number on the number key. We're leaving this blank. This right here means frequency list. We're leaving it blank. Go down to calculate. Now I'm going to hit enter and stuff's going to happen. And it is beautiful stuff. It is beautiful. I'm going to tell you what each thing means. And some of that we will never use, and I have never used, but it could be useful for somebody. But I'm just going to go through the top few, and I'm going to leave the rest for Tuesday of next week, but I'm just going to go through the top few. So this top one, our calculator assumes every data set we put in is a sample. So it gives sample mean. It gives us X bar. And this was the sample mean. This is the mean that we calculated. We calculated that our mean was 79. I love when that happens, when we get the same number. So this one has our capital sigma X. This just means add all the X's up. Add all the variables up. If I added all 10 of them up, I get 790. And I don't know why they think that we need this, but if I added the squares of each number up, I would get this right here. I've never used this one. It's just there, and I'm like, okay, it's there, whatever. And I just move past it. I've never used sum of x squareds. Never. This right here, this top one, is the sample standard deviation. We did not calculate that because we assumed our data set was population. But see, SX, you're going to want to write that down in your calculator. SX is the sample standard deviation. So that's beautiful, 10.3. Sigma, this is my baby sigma, my little lowercase sigma, sigma x. This is the population standard deviation. If you can't remember which is which based on the symbol, just remember the sample is always going to be a little bit bigger than the population. Sample's always a little bit bigger. So if you can't remember based on symbols which is which, sample's always going to be bigger. This is exactly the number that we got. We got 9.82. You can look in the chat. It's right there. So that's good. I love when our answers match the answers that we did by in the calculator. This is perfect. And then right here, and n equals 10, that is says that we have 10 data values. This is my sample size. It assumes it's a sample. So if we have a population, then just pretend that's a capital N. This right here tells us our minimum value. Our minimum was 62. If I scroll down, I'm going to ignore a few of them because we're going to talk about those on Tuesday. This bottom one tells you the maximum value. These three in the middle, ignore those. We're going to do those on Tuesday. Any questions about this? All right. So that's how to use the calculator. Do you guys want me to do the commuting data? Do you want me to do that, the travel times, to do one more? It's up to you. Or if you feel good, then we're good. Yes, do that one. Okay. All right, Kiana. We will. Your wish is my command. All right. So what I'm going to do is I'm going to put the data in just in case some of you don't have your PowerPoints printed. I will put the data in, but then I'm going to let you get ahead of me on this and see if you can attempt to do it on your own. If don't worry, we're just going to go with one list for now, Kevin. We do have next week, Thursday, we're going to talk about more lists. So if you can hold on till next week, Thursday, then um, then please do. So put a pin in that, please. All right. So I'm going to go to stat and then edit, and I'm going to clear this out. Remember to clear it out. You arrow up to L1 and hit clear, enter. That way it clears all your data because we only have 7 this time. I'm going to put these numbers in here, and then I'm going to let you get ahead of me. So I want to see if you could do this on your own. Okay, I'm going to put that in. Go ahead and see if you can run your one variable statistics without me. Okay, I'm going to now. Okay, good. Thank you, Amanda. I'm going to walk through it for those of you who may have gotten lost or weren't able to do it. I don't expect you to get it the first time, so I'm going to walk through it again. All right, we already have this in here. You can hit stat, arrow over to calc. We want the first option, one variable statistics. L1 should already be your list. So we can just arrow down to calculate, leave the frequency list blank, and hit enter. We got 24.9 for our mean when we were calculating it. That's fantastic. I'm going to go back a couple pages because how come all my stuff is gone? Where did it go? Oh, wait, no, here we go. And I got 11.36 for the population standard deviation. Yay, I love it. I love that I see that you guys are getting it in the chat. Yay. Victory makes me happy. And if this is my sample standard deviation in case I needed it, there's the sum, got all that crazy good stuff. All right, good. I am very, very happy that we're using the fancy schmancy. I totally understand. And I am happy to actually, you can always just come back to the video and watch it again. That's one of the nice things about the video is you can come back and watch it again. The one on the Zoom video is better because I'm walking through it as I'm clicking on it. I feel like the pre-recorded video just has snapshots of my calculator on it. I don't think that it has the video of me actually walking through it. So find it in the Zoom and just rewatch it if you need to. Or if you really need me to walk you through it again, I can do that in messages as well. Okay, I'm going to go back to my PowerPoint because, it's what we do. Go back to the screen we were on. So I don't know why. Is that even there? Did I even draw one? I didn't. I think that this is just a random page in there. So I'm going to go through that. Okay. So we're going to calculate, actually, we're going to take some standard deviations and we're going to compare it. So one thing that we use standard deviation for is to figure out how reliably we can predict something or how consistent something is. Because a smaller standard deviation means that whatever data we're collecting is pretty consistent data if it's a smaller standard deviation. A bigger standard deviation tends to be that it is all over the place. So I have two data sets right here. Now in my brain, these wait times at Wendy's and McDonald's are the drive-through. Probably because I very, very rarely eat inside of a fast food restaurant. Actually, I'm not big on fast food anyway, but I do have grandkids and they do kind of like their Happy Meals. So, um, these are in my brain, these are wait times in the drive-through. So that's what I'm assuming, and that's what I'm going to say. So these are wait times in the drive-throughs at Wendy's and McDonald's. And somebody collected all this data. I don't know how many it is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So it looks like 30 of each. So they took 30 of each of these wait times and they calculated the standard deviation. So the standard deviation of Wendy's is 0.738 minutes. Standard deviation of McDonald's is 1.265 minutes. So the standard deviation for McDonald's is bigger. Now, this doesn't say anything about what the wait times are. It just tells me how spread out they are. Since Wendy's has a smaller standard deviation, it is more predictable. It's a more predictable wait time. The range of their wait times is smaller than the range of McDonald's wait times. So you might, if you're at McDonald's, you're not going to have a very good guess of how long it's going to take you in the drive-through. Whereas Wendy's, you're going to have a little bit better guess of what it's going to be. So if you're looking for consistency in wait times, you'd go to Wendy's. If you don't care about consistencies and you just want the Happy Meal toy, go to McDonald's. All right. So, your homework will ask you for variance. Your homework treats variance like it is a really important topic and it will greatly change your life. If you know about variance, you're going to win the lottery. You're going to win whatever election you're running for. You're going to get straight A's. You're going to rule the world. That's the way the homework acts, like variance is that important. I have never in my entire life used variance for anything other than a homework question. I don't know why it is important. This is another thing. If you can figure out what makes variance so important and why everybody tells us it's so important, you can post that in the forums and I'd be really happy to see what it is because I have not found a good use for it. So there's my soapbox and I'm going to jump off of it. Now I'm going to tell you all that variance is taking the standard deviation and squaring it. So just square the standard deviation and you have variance. Your homework will ask you for variance and you'll put it in and feel really proud of yourself for getting it right. Then you'll never use it again. I will not be testing you on variance, but the homework will say it. homework will ask you for variance. So there you go. Variance is just the standard deviation squared. All right, there we go. And I really hope my personality doesn't get me in trouble when I'm observed on Tuesday. They should appreciate it. They should appreciate that I am at the um, high school for 11 hours and then come here and teach. But I enjoy this. This is fun for me. This is my idea of a fun time. All right. So, empirical rule. This is a whole lot of words. I am going to use these words again in a way that's going to make more sense than having them a big wall of words like this. But I'm going to tell you the empirical rule is pretty darn important. There's going to be a diagram that the diagram is more important than like if you're going to tab something, don't tab this page, tab the diagram, and I'll talk about it and all of that in a minute. I draw it so frequently. It's kind of like I'm like, okay, let me make a sketch of the empirical rule. Anyway, so what the empirical rule tells us is if we have a nice bell-shaped distribution, so you remember what the symmetric bell shape look like, 68% of our data will be within one standard deviation of the mean, which means if I take that standard deviation we just calculated and I add it to the mean, create a barrier there, then I take that standard deviation and I subtract it from the mean and create a barrier there, 68% of my data is going to be within those two barriers. The 95% of my data is going to be within two standard deviations of the mean. So if you multiply the standard deviation by 2, then you add it to your mean, put a barrier there, multiply the standard deviation by 2, subtract it from the mean, put a barrier there. 95% of your data will be within those two barriers. So it doesn't matter. It's the same for sample data um, and population data. It just is going to change your symbols. It's just prettier symbols with population. All right. So this is the diagram. Now, in the past, many of my students have told me that what has been helpful is to print this beautiful diagram off, put it in a sleeve protector, one of those page protector things, and then get a dry erase marker because you're going to be labeling this a lot. So you could keep drawing it and drawing it and drawing it over and over like I do, but we all know I'm a little bit crazy. So smart people who aren't a little bit crazy like me, or maybe if you are crazy, who knows, will put this in one of those page protectors, those sleeves, and get a dry erase marker and just write on it. It is super, super helpful. Okay, so as I said, 68% of my data. So if I subtract the standard deviation from the mean and I add the standard deviation from the mean and I have that little area, 68% of my data is going to be in there. I'm going to erase these. 68% of my data will be within that one standard deviation. So this is the mean right here. This red line that I just drew really poorly. That's the mean right there. It is smack dab in the middle of my bell curve. So I've got the 34% here from to the left of my mean down to one standard deviation below. 34% here to the right of my mean up to one standard deviation above. All right. So then move two standard deviations out. We've got this right here. Okay, that's really ugly. I'm gonna fix it. Wait, let me see. Nope, it didn't work. Pretend that's a nice, pretty, perfect rectangle. Okay, 95% of my data is within two standard deviations of the mean. 95%. Now let me tell you, this is where, uh-oh, that was ugly. Let me fix this. Okay, in here, I'm gonna highlight it. I like highlighters. Highlighters can be pretty. Maybe, okay. In here, these are all where your usual data lies. Anything outside of that 95% is considered an outlier. So in here, this is not unusual. Uh-oh. Not unusual. That's really ugly writing. Let me write it again. Not unusual. Those are not unusual. Those are where the usual values lie, or things that are not unusual. Maybe expected values would lie there. Now, 99.7% of the data is within 3 standard deviations of the mean. So if I took the standard deviation and multiplied it by 3 and added that to the mean and put a barrier there, take the standard deviation, multiply it by 3 and subtract it from the mean, put a barrier there, then 99.7% of our data is going to be within those boundaries. Now, anything else, that 0.3% is going to be beyond 3 standard deviations. It could be quite far, and anything beyond 3 standard deviations is that 0.3%. So anything out here, I'm going to find another highlighter because they're fun. So anything out here, anything in my squiggly orange area, all of that stuff is outliers. Outliers, outliers. Anything out here would be an outlier. Anything out there is unusual. We would not expect to find stuff out there. There will be some stuff out there, but anything found outside of that 2 standard deviations, outside of the 95%, is considered an outlier. It's considered unusual. Okay, I'm going to mention this 5,648 more times, but this is the first time you get to hear it. So I say it a lot because it's important. If it's important, I keep saying it. All right, I'm going to erase all of this because this is a whole lot of writing and we want a nice, pretty picture. So, as I said, you're going to use this diagram a lot. So putting it in that sheet protector is a really good idea. It's okay if you don't. You can just keep drawing it, or you can just print multiple copies of this. You know, that works too. Maybe print multiple copies, like 2 to a page or something, and then use them. And it's also a good thing to use. I've had many people on the first test just have a printed copy of this, and they do some of the work directly on this and then include it with their test work. That's fine too. I'm cool with that. All right, moving on. I'm going to do an example where we have some numbers. So the following data represent the serum HDL cholesterol of 54 female patients of a certain family doctor. So they just took 54 patients and they wrote down their HDL cholesterol, which I don't know what serum HDL cholesterol is, but it sounds important. And so this is just 54 female patients. This is a sample. So I'm going to move on. Okay, we're going to figure out the population mean and standard deviation. I'm going to give that to you. And we're going to do a histogram and make sure it's bell-shaped. I'm going to give that to you. And then we're going to label our empirical rule, our normal curve, and we're going to answer some questions. Okay. So our population mean is 57.4. Our standard deviation is 11.7. Now, this is not a perfect bell curve, but as I said before, statisticians don't deal in absolutes. It is absolutely close enough. It's close enough to a perfect curve, and I can draw a bell over it, kind of, sort of. I mean, we look like we're slightly right skewed, but not terrible. So we will accept mostly bell curved or mostly normal. Okay, so we have the mean and the standard deviation, and we have our histogram. Now we want to know, so we know that it's supposed to be 99.7% of all of our serum HDL patients, all of these patients, their data will be within 3 standard deviations of the mean. We're going to do a little bit of other calculations though. All right. Here's my bell curve. This is what you're going to be using it for. You're going to get a data set. You'll have a mean and a standard deviation. You can label each section. So our standard deviation was 11.7. So what I did is I took 57.4, I added 11.7, which is my standard deviation, and I got 69.1. So I know that 34% of my data should lie somewhere in between there because that's one standard deviation away. I added 11.7 again to get two standard deviations away. I know I lost my decimal point so that I could get 80.8. So I know that 34% plus 13.5%. So 47.5% of my data I would expect to be between the 57.4 and the 80.8. Hopefully you're picking up what I'm throwing down. So once again, I added 11.7 to get the 3 standard deviation away mark. This is how we label our curve. Now I'm going to go the other direction. I'm going to subtract 11.7 and I get 45.7. Subtract it again and I get 34. And I subtract it again to get 22.3. This helps me to get all of the intervals on my empirical rule, my beautiful diagram here. So I got all of those intervals. So what we're being asked, I'm going to get rid of this. I'm going to get a highlighter because it's fun. Who doesn't have fun coloring with a highlighter? We want to know the percentage of all of our patients that we would, sorry, the percentage we would expect to be between 34 and 69.1. So I'm going to highlight all of those sections. There's that one, this one right here, this one right here. What is it? That's it. So these are the sections on my diagram that are between 34 and 69.1. So we're just going to add those 3% together. So I have 13.5%, 34%, and 34%. I'm going to add those together. I probably could do it in my head, but it is 6:30 on a Thursday night, so I don't really trust myself. So we have 81.5%. So we would expect about 81.5% of all of our patients to have their HDL serum HDL between 34 and 69.1% or 69.1. I don't know what the units are, but this is what we would expect. Now, these numbers are not exact. I'm going to teach you ways to get the exact numbers later on. But the nice thing is that this is a really great way to estimate it because we don't always want to take the time to take out our calculator and do all of the math if we can just quickly say, oh yeah, it's about this much. And sometimes an estimate is really all we need. Now we're going to go back and we're going to figure out the actual. We're going to look at the data and we're going to find the ones that are between 34 and 69.1. And we're going to see how close we are. So I'm going to jump back. I'm going to write the numbers down because otherwise I'll forget. So it was 34 and 69.1. These are the numbers we're looking at between. I'm just going to circle them. It's going to go through and circle them. It might be easier to cross the other ones out actually because there's fewer that are not between those. So I'm going to cross the ones that don't work out. All the 70s are gone. Okay, is that it? Those are the only ones I'm missing? Okay, so we were at 54. I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 of them are not. So we have 45 out of 54 that are between that. 45 divided by 54. This gives me 83.3%. I'd say that's pretty darn close. We had 81.5%. This is 83.3%. I would say that is a pretty decent estimate. Okay, I'm going to go back over here. Any questions on using the empirical rule? I'm going to go into the homework and show you one of the homeworks, but I want to know based off of this, any questions on the empirical rule? Okay. I'm going to go back to the main diagram right here, this beautiful one right here. I'm going to go back here and then I'm going to pop over to my open math and we're going to look at a homework question. So I feel like that's always helpful. Maybe. Come on. It doesn't want to play today. Okay, all right, so let's go to 3.2. You're going to have some empirical rule questions. Let's take a look. Okay, those are standard deviation questions. Let's jump down. Just keep scrolling, keep scrolling. Okay, I mean, those are there, but I want to kind of, so this one right here, I just want to show you, this one already has it labeled. So this would be the mean, and this would be one standard deviation below and one standard deviation above. This would be a really good case. I'm just going to label mine on my graph and pop over and show you. I like when it's already labeled, but let me see, 15, 15, 1095. So if you have this paper and a dry erase marker, it's really quick to just label it like this. Okay, move that. Just to label it like this. So when it asks you questions, you can just add those percents together. Because that's all you're doing is if it wanted to know what percent would you expect to be between 1305 and 1515, you would just take these 2% and just add them together. So having it labeling your diagram is helpful because what they give us, they don't show us the sections with the labels. So if you just label your diagram, or you can sketch one real quick, but without a lot of practice, if you haven't been doing it for years like I have, it takes you a little bit more to sketch it. So having this is helpful because you just label it along the bottom and then it might ask you another question. What percent is between 990 and 1305? Then you would add these three together. So you already have those labels in the section. So it's super useful. Okay, let me go back again. I know there was a specific question I wanted to show you. I just don't remember where it is. Where am I? Oh, that's because I'm not on the computer. I'm on the iPad. Silly me. Silly me. Okay, maybe the question was somewhere else. Okay, but this right here. Okay. Acme Company manufactures widgets. The distribution of the widgets is bell-shaped. The widgets' weights have a mean of 43 ounces and a standard deviation of 4 ounces. Okay, so mean of 43 and standard deviation of 4. So you would jump back here and you would say, okay, what are my numbers? 43 and 94. Okay, so you would just put, or 43 and 4. So put 43 here. And then you just add, that's 47, this is 51, this is 55, this is 39, 35, 31. You have it all labeled, then it's really easy to answer the questions. 95% of the widgets lie between what? Look here. Okay, I see 95% of my widgets are between 35 and 51 because that's the 95% interval. Then it says, what percent would lie between 31 and 51 ounces? So I've got that. There's 31 and there's 51. Add these percents together. This is the best way to use this tool, if you ask me. And so it just makes it a little bit easier to answer these questions. All right, this is all I have for you today. So you can go ahead and ask me anything for while we're on the recording.
Can you just go over that one more time for me?
Okay, which part?
How you did,
How I
where
labeled it?
yeah.
Okay, no problem. Okay, so I'll
Like
start.
taking the bell shape that we were given and stuff and how you labeled it onto this one.
All right, perfect. I can do that. Okay, so this is our given bell shape. So right here, it says that this has a mean of 43 and then a standard deviation of 4. Okay. My mean always goes in the middle. So 43 always goes in the middle. So going to the right for each interval, I'm just adding the standard deviation. So adding one standard deviation, 43 plus 4 gives me 47. So 47 goes right there. That's now one standard deviation away. I'm going to add 4 again to get two standard deviations away. 47 plus 4 is 51. And then once again, to get three standard deviations away, 51 plus 4 is 55. Now I'm going to go the other direction. 43 minus 4 is 39. I'm just subtracting 4 now because now I'm one standard deviation below. So I'm going to subtract 4 again, and I get 35. Subtract 4 one more time and get 31. Okay. Do you need me to go through how I find the percents and all of that also?
No, I got it from there.
Okay. It was just the labeling. I went too fast.
Yeah, I just got distracted.
No problem. Sometimes I get excited. When I love the math, you guys can tell I'll get really excited and I start going too fast, and everybody needs to just slow me down because I get excited. I just one of those people that gets excited about the math, and I apologize and don't apologize all at the same time. Okay, more questions.
I had a question on the homework.
Okay. On the
Um,
previous homework or
yeah, this homework. I don't know if yours looks the same, but I think it was question 7 that I was getting confused on.
on the 3.2?
Yeah.
Okay, this one right here.
Yes.
Okay, this is the other one I wanted to go over. Thank you for that. So this is pretty much just a common sense question. So you're thinking about, so we know that 95% of our data is within two standard deviations of the mean. So two above and two below. So we're looking at if my average is, yours might look different. There's a couple of different questions out there, but they're all basically the same thing. There's one about professors or something. So if I know that my crowd is 21,000 fans, if I think about it, do I really think that 95% of the number um, of the crowds are only 40 fans away from 21,000? Probably not. You got to look at what makes sense. Do I think that I could, that um, my standard deviation is going to be 20,000 fans. So I would add 40,000 fans to 21,000, subtract 40,000 fans from 21,000. You're just trying to think of which one makes sense in the grand scheme of things, comparing it to the average. It's really just a common sense thing and seeing which one makes the most sense. If that helps. So you're just kind of thinking about your bell curve and your empirical rule and which one's going to make the most sense. And I'm your explanation on it, as long as you're saying that it makes sense that 95% of my data is between these two values, as long as you say something like that, talk about the 95% is like the number we refer to the most. So if you talk about that in your explanation and just common sense, I don't know how to explain it even better without giving you answers. But I can tell you it's probably going to be either 200 or 2000. Yours might be different, probably have different numbers, but all right. Other questions for while we're on recording?
I had one more question.
Okay.
Okay, so you know in standard deviation where you square the values when you add it up, so to get rid of the negatives?
Yes.
I was wondering if there's a reason we don't use the absolute values of the numbers.
Because some old man somewhere a long time ago decided this is the way we were going to do it, and so we did it. I don't know. I don't have a better answer.
Okay, fair enough. Thank you.
I'm sorry. It's just, I mean, really, that's kind of the how things happen is somebody discovers this and they probably tried it both ways and was like, you know what, squaring it and then taking the square root later was more accurate. I don't know how their sometimes I'm just like, I'm just a worker bee. I'm just going to go with it. So I'm sorry I can't be more specific on that, but that's what I got.
Thank you.
You're welcome. Anyone else? I'm going to turn the recording off and we will have questions off the recording.